Now, let's continue the example by making the assumption. So let's say that instead of stopping there, they told us that the initial conditions were r0 equals 2 and r1 equals 3. Well then, all we have to do is plug in to find out the remaining values. If r0 is equal to 2, we know that that's c times 3 to the 0 power, we're just replacing n with 0, plus d times negative 4 to the 0 power as well. And then r1 is equal to 3, which is c times 3 to the first plus d times negative 4 to the first. So using what we know from algebra, solve this equation. So let's take a look at what this gives us. This tells us that 2 equals c plus d, and that 3 equals 3c minus 4d. Well, this is just a system of equations with two unknowns. You can solve this by substitution or elimination, whatever you're more comfortable with. We'll just go by elimination here. Let's see, if we plug in, let's multiply the top equation by 2, by 4 rather, and that will give us the 4's to cancel out. So multiply everything by 4, so that is 8 equals 4c plus 4d, which when we simplify, this is 11 equals 7c. Those cancel. Now if 11 equals 7c, then c has to equal 11 sevenths. And then what does d equal? Well, plug in to find out. 2 equals 11 sevenths plus d. So we subtract over, so you have 2, let's make that a common denominator of 7, so it's 14 over 7 minus 11 over 7 equals d. So d has to equal 3 sevenths. How do we know that we've done this correctly? 3 and 11 is 14 over 7 is 2. So then plug in to finish this up. We know that r sub k, or r sub n rather, let's use r sub n. We know that r sub n equals c is 11 over 7 times 3 to the n plus d is 3 sevenths times negative 4 to the n. So what we have found here is an explicit formula for the recurrence relation above with given initial conditions. Using what we've just learned, we can also do this for the Fibonacci sequence. The Fibonacci sequence is defined by the two previous terms, where we know that f0 is equal to 1 and f1 is equal to 1, such that fn is fn minus 1 plus fn minus 2. Now, if we look at what we have, a is equal to 1, b is equal to 1, so we go through our characteristic polynomial. We have t squared minus 1t minus 1 equals 0. And this is something that does not factor, so we have to go ahead and use the quadratic formula for this. So we have t equals negative b, which is 1, plus or minus the square root of b squared is 1 minus 4 times 1. So 4 times 1 times negative 1 all over 2 times 1, which is just 2. So t equals 1 plus or minus the square root of 5 over 2. Now, what does this tell us? Our roots are distinct, and we know that t is either equal to 1 plus the square root of 5 over 2, or t equals 1 minus the square root of 5 over 2. We can go through the rest of this process and set up our linear combination. And since we know the initial values, it's definitely messy to do this by hand, but it's manageable if we have to. Okay, So let's play around with this a little bit. We know that the Fibonacci sequence f sub n is equal to c times 1 plus square root 5 over 2 to the n plus d times 1 minus the square root of 5 over 2 to the n. This is where things get a little bit hairy. So if we plug in our initial values, we have f0, which is 1. When you plug in zeros, you get just c plus d. And f1 is also equal to 1, which is each of these are intact, right? So we have those as coefficients. 1 plus square root 5 over 2 times c plus 1 minus square root of 5 over 2 times d. Now, if we want to use, whether it's elimination, substitution, whatever floats your boat here, again, it's going to take some fancy footwork. So let's say we multiply this first one by, I don't know, negative of this thing here. So we have negative 1 plus square root 5 over 2 equals negative 1 plus square root 5 over 2c. It's going to allow us to cancel those out, plus the negative, so let's just change that to minus 1 plus square root 5 over 2d. Start canceling out what we can here. This cancels, this cancels. So we have 1 minus this thing. So that's 2 over 2 minus, distribute that negative, so we have all of this over 2 minus 1 minus square root 5, right, equals the c's went away. And then we have d times, they're both over 2, so we have 1 minus square root 5 minus this thing, right? And again, these are all over 2. So then it's minus 1 minus square root 5. Okay. So if we go ahead and simplify best we can, we have 1 minus square root 5 over 2 equals d times 1 minus 1 is 0. This is minus 2 square root 5 over 2, which is just negative square root 5. So we know that d equals 1 minus square root 5 over 2 divided by the square root of 5, the negative square root of 5. So it's the same thing as multiplying by 1 over square root 5. Again, that's negative, so I'm just going to pull that negative out front for now. And we have to clean this up. So we have to rationalize the denominator. So square root 5, square root 5. That gives us negative 1 minus square root 5 times the square root of 5 all over 2 times 5 is 10. In the home stretch at this point, d equals, distribute the square root, so we have negative square root 5 plus square root of 5 times square root of 5 is just 5 over 10. And this is what d equals. So if we want to get c, we know that c plus d equals 1. So go ahead and plug this in, and I will let you finish this example from here.